Okay, in this video I'll go through some IIR design examples. This is a reminder from lecture of why we would do this. We basically have analog filters we want to convert and use in DSP, and these are the steps: stating the specs, converting it to continuous frequency, design an analog filter. That basically means pick the filter parameters, and then map things back, and we will use the bilinear transform. Again, from class, here's the bilinear transform. It lets us go from h of s, the Laplace transform, where we can describe an analog filter, to h of z, where we can describe a discrete time filter. If you remember, s is given as some real part, plus j big gamma, where this is the frequency, the continuous time frequency. So the regular Fourier transform, the continuous time Fourier transform, is the values along this axis, are the values along that axis. In discrete time we have z plane, real z, imaginary z. Here's a unit circle. The discrete time Fourier transform is more or less the values along the unit circle, and here's some particular omega. So we basically went through how you map from s to z. There's also a frequency mapping. We go from discrete time frequency to continuous time frequency. That involves the sampling period. Capital T is 1 over fs. And the thing to notice, we have basically three different things in play here. We have the continuous time frequency, we have t here, where we can say t is 1 over the sampling frequency, and we have this thing. So in all these problems, we're going to use this formula to map the frequency, and basically we'll it's kind of plug and chug. We'll figure out which of these we know, solve for the ones we don't in terms of those, and then we'll use this to convert h of s to h of z. That's the general idea. The first case is where we have some general form for h of s, and we also have some values for what we want our digital design to look like. This case is a single pole low pass h of s, but we might say, for example, a more complicated example would be that we want a ninth order Butterworth, for example. Before talking about the DSP part, let's just look at this filter. The magnitude squared of this is h of s conjugate. On the frequency axis, we can say s is j omega. So we plunk that in here. We get a j omega for the s. We get a minus j omega because of the conjugate. And that turns out to be this thing, omega c squared over omega squared plus omega c squared. At the cutoff frequency, omega is equal to omega c, we get a half, which is minus 3 dB. So this is the minus 3 dB point. And we're saying here we want, in digital, that minus 3 dB point to correspond to this frequency. Okay, so how do we do this? How do we make this transformation? There's basically two steps. One is we use this frequency mapping, and then the other one is we're going to plug in for s, we're going to plug in this expression for z we calculated earlier. The first one, if we just copy down that formula, we have the continuous time frequency is 2 over t tangent discrete time frequency divided by 2. Here we want to map a particular frequency, the cutoff frequency, so I just put a c on each of these. Omega sub c is this, plunk that in there, divide by 2, and we find that here of these three things, this, and this, we knew this, so we can calculate that the continuous time cutoff frequency is 0.65 over t, where again that's 1 over the sample rate. So now we have this, and this is kind of designing our filter parameters. Now we can say, let's just substitute in our expression for s. So s is 2 by t, 1 over 1 minus z inverse, 1 plus z inverse, just substituting in there. Where I had the cutoff frequency, I put in 0.65 divided by t. Now the interesting thing here, which holds true in general for this case, is that the t cancels out. That's kind of a general thing that happens for this type of problem. And so we get something here where the design does not depend on sampling frequency. Okay. So for example, if you go in MATLAB and you say, as you did for one of your recent projects, BA is butter 2 0.2. This would design a second order Butterworth with 0.2 pi as the cutoff. If you do this in MATLAB, you never say what the sampling frequency is, and the reason is it's doing this under the hood. Sampling frequency divides out, the t divides out. Okay, once we have this h of z, we can do pole zero plots, we can do inverse z transform, and we'll get our filter coefficients in the time domain. Those are the b's and the a's that MATLAB gives you, or whatever language you choose to use. Okay, the next case, I went too far. The next case is where we have a specific form for h of s, and we have values at some important frequencies. It's different because it's specific and not general. So here, the specific case would be this. Let's say someone gave us this. We had an analog filter, took the Laplace transform, and this is what it looked like. And let's say we want this to be a resonance, give a resonance at a digital frequency of pi by 2. Well, what do I mean resonance? If we look at this filter, we have to analyze it a little bit. I can plug in j omega for s, and that gives me this here. I can multiply out this term, and I get a minus omega squared, a constant, and then a cross term here, plus 16, and the top just goes to that. If I look at the bottom here, this term and this term I can write as 4 minus omega, 4 plus omega, and then I have this stuff left over. You can see if I didn't have this 0.1 term, then these terms would go away. On the bottom I would just have these two, and I would get a 1 divided by 0. I'd get an infinite response at plus or minus 4. The fact that I have a little bit of offset here moves the pole off of the frequency axis, and I get a little bit of damping. But this is basically a resonance at omega equals plus or minus 4. It's a resonant filter. And you can figure out that's a frequency of 2 divided by pi hertz. So like roughly 2/3 hertz. Okay, so that's just looking at this filter. Now we say we want to use the bilinear transform. Again, we're going to use frequency warping, and we're going to plug in s. Okay, so here's the frequency warping equation, just generic equation. The difference is now, before we only knew we only knew the omega. Now we actually know two things. We know that the resonance of the analog signal is at 4. So where I have this, I put in 4. And I'm saying digitally, I would like that resonance to be at pi by 2. So where I have omega, I put in pi by 2. And then I have an equation I can solve down for t, and it turns t should be half a second, which means the sampling frequency should be 2 hertz. So this is slightly different. In here, instead of t dividing out, actually t is what we solve for, and the only way we can make this problem work is if we set a particular t, which gives us a particular sample rate. Now I can take the h of s. Wherever I have the s, I put in that formula, 1 over 2 over t, which is 2 over a half, times my ratio of things here, plus 1. Here I'm dropping it in. Here I'm just noticing that 2 divided by 1/2 is just 4. So these are the same, but I'm writing as 4. Now we've got something where we could manipulate this. We could find pole zero plots, do the inverse transform, and so on.